inviting me and giving me the opportunity to present our work here. It's on how to enable safe handover tasks between different levels of autonomy in highly automated vehicles. So, right, first experiments involving autonomous vehicles have begun almost a century ago. So many have predicted that we will have fully autonomous cars on our streets by now. I'm referring to Rodney Brooks' plenary talk at ICRA2020. Commercially available vehicles today have maximum level 2 autonomy. So the driver is required to take control occasionally between different levels of autonomy when required to complete an end-to-end journey. These handovers between the car and the driver cause safety concerns, as the driver might not be fully aware of the surrounding situation and the enabled autonomy features instantly, as recent incidents suggest. We have taken inspiration from this video by General Motors from 1956. This was General Motors' vision on how the driver changes between manual control and full autonomy. Imagine that the man in the tower represents the artificial intelligence of the autonomous car here. So the transition to the autonomy level is intuitive, human-centered, and safe. We propose a new interface designed for highly automated vehicles, measuring the situational awareness of the driver through physiological and behavioral sensors, giving appropriate feedback through a soft robotic driver seat acting as a co-pilot, and by that allowing safe, coordinated, and timely transitions between different levels of autonomy. An important aspect of the transition between autonomy levels is situational awareness, consolidating data into an understanding of the situation to achieve a safe and timely transition. Ansley differentiates the state of attention and defines situational awareness under 3 levels: perception, comprehension, and projection. Perception is about collecting critical data through 5 senses. Comprehension is the traditional information processing, and projection is about prediction of future states of the decision-making process. In order to measure situational awareness, we looked into identifying the correlation between situational awareness and EEG signals of the brain. The results demonstrate a positive correlation between the power spectrum of beta and gamma and situational awareness, as it can be seen in the figure in the bottom right. Beta is responsible for attention and alertness. Gamma is associated with cognitive functioning and information processing. And as you can see in this figure, a strong activation of neurons in the left and right hemisphere is observed. These areas are responsible for vigilance and intuition, as well as logical and linear thinking. To intuitively increase situational awareness, we are creating a soft robotic driver seat. This work includes the creation of a novel hybrid actuation system that allows to simultaneously switch between pneumatic and hydraulic actuation to independently control position and stiffness of the seat. So I developed a soft robotic actuator with embedded pre-compressed foam and 2 inlets for water and air actuation. As you can see here, it is possible to either fully actuate the robot using water or air, a combination of both, or change the ratio of pneumatic and hydraulic actuation. Currently, we integrate this work into a driver seat to prepare experiments in the Land Rover Jaguar driving simulator as soon as the situation at the moment let us do that. Future work will explore how to detect situational awareness, the integration of more soft robots into our seat, and a number of experiments. If you're interested in our work and would like to discuss this in more detail, please feel free to ask questions now or contact us via the Slack channel, via Twitter, email, and wherever you can find us. Thank you very much.
So thank you, Jan. I think in interest of time, we can postpone, let's say, the questions to Slack workspace.
Yeah.
So people may ask questions there, and then you can answer them.
Yeah, I'm happy to take questions then. Thank you very much.
Thank you again. So the next speaker is, I think, Raf Rahal from University of Rennes. She will present Haptic Shared Control for Enhanced User Comfort in Robotic Telemanipulation, an abstract by Raf Rahal, Giulia Matarese, Marco Gabbicini, Alessio Artoni, Domenico Prattichizzo, Paolo Rubuffo Giordano, and Claudio Pacchierotti. Raf,
Hi, thank you, Mario. So I'll share my screen now. Can you see it?
Yeah.
Okay. So I'm Rahaf Rahal, and I'll be presenting our new method on haptic shared control for enhanced user comfort in robotic telemanipulation. So starting with the motivation behind our work, haptic shared control has been used a lot in the literature to share the control of the system between a human and a robot component. It has been used, for example, to do different tasks, such as guiding a user along a trajectory or to a desired point, or even away from undesired regions in the environment. However, none of the previous work focused on the user's comfort during telemanipulation, even though this is a very important issue in many applications that require long or repetitive tasks. A few works exist on the topic in the field of human-robot interaction, but not in teleoperation scenarios. So our main contribution in this paper is basically to present a haptic shared control technique that minimizes the user workload during robotic teleoperation. We start by devising a new online metric that is based on the Rula estimation, commonly used in ergonomics to estimate the human upper body's effort. Then, using this metric and an inverse kinematics implementation of the human arm, we can estimate the user workload online. This workload is then used, along with information that we have about the task at hand, to generate haptic active constraints. These constraints guide the user towards accomplishing the task while also minimizing the physical workload required. So to calculate in real time the workload value, what we do is we assume the user's shoulder is fixed, and we assume that we know the pose of the wrist of the user given the position of the master device. And then using inverse kinematics and without any external sensor, we can actually estimate the arm angles. And then we can calculate the workload value, which is basically the deviation from the resting pose. So for example, you can see to the left a picture of with a low value of W, which is basically comfortable for the user, and to the right, a less comfortable pose with a higher value of W. The haptic feedback is then designed as the weighted sum of two terms. The first one is FW, which basically minimizes the workload W. And the second one is FR, which minimizes a task-related cost function. So for example, it could be related to the distance to the target or to the deviation from a certain trajectory desired. In our work, we chose as a representative cost function the distance to the target in a pick-and-place task. And of course, alpha and beta are weights, which are designed, and they can depend on the task at hand. For example, if we have a long task, which requires more user comfort, we can increase the value of alpha. So here we show as a representative example, a simple task of moving the robot from a point A to a point B, which are basically at the same height. So you can see with a value of alpha equals to 0, the user is guided along a straight line because it basically is the easiest way to minimize the distance between the 2 points. As alpha increases, you can see that the user is guided towards a more curved path in order to minimize the user effort while teleoperating the robot. So we tested our system for values of alpha equals to 0.2 and 0.4. And you can see that the higher the value of alpha, the more curved the path is. So I don't know why it's not playing. Yeah. Okay. Sorry about that. Then we tested our system in a user study with 15 participants. And the task was basically a pick-and-place task that is shown in the video over here. We tested the system with different objects and with different poses per each object. And we also chose different values of alpha to see the effect on our algorithm. So the results basically showed that as we increase the human-related component in the haptic feedback, the user comfort is improved by 30% as shown by the NASA TLX test results. But at the same time, we had a slight decrease in the performance in terms of completion time and placing error. As a summary, we presented a haptic shared control method that takes into consideration the human comfort in robotic teleoperation. So we present a haptic feedback for the user that takes into account at the same time a human-related and a task-related cost function. Thank you for listening, and I'll be happy to take any questions.
Yeah, thank you, Raf, for your talk. Actually, like we are setting up, since it seems that we are a bit late in the Slack channel, like a thread for each speaker, so that if they have questions, they go to the Slack and then you can talk on that. So thank you for your talk. And then introduce the next speaker that actually has a recorded video. It's a joint work between the MIT, the University of Texas at Austin, and Ohio University. And it's called Control and Planning of Variable Stiffness Links for Inherently Safe Physical Human-Robots Interaction. And it will be presented by Hushi, that, as you can see, he will present virtually the contribution.
Thank you for watching this video. This material is a video presentation for the ICRA2020 Workshop, Shared Autonomy, Learning and Control. Today, I'm going to present control and planning of variable stiffness links for inherently safe physical human-robot interaction. My name is Yu She. I'm a postdoc from MIT. Collaborative robots, they are designed to share workspace with humans, and they will physically interact with humans. Therefore, the safety becomes a very important issue. We would like to develop a safe and performant collaborative robots. Here we present variable stiffness link to demonstrate this idea. We consider the head injury criterion to evaluate the potential impact results. The smaller value, the safer. The HIC is affected by the impact velocity, the robot stiffness, and the effective mass of the robot. Basically, we want to dynamically control the robot stiffness based on the robot velocity, such that the HIC value will be lower than a safety threshold. Here is a prototype design. It is a variable stiffness link with layer jamming. We can control the pressure of the vacuum bag to control the stiffness of this link. We also developed a dynamic model of this link based on the super-rigid body model. We developed a motion controller using the input-output feedback linearization. And here is the nonlinear system dynamics based on the super-rigid body model. We choose the top here, and we can formulate the closed-loop system dynamics. Then we can design the control law. This controller requires very accurate dynamic modeling, which will be very challenging. To address the uncertainty, we propose to use the extended state observer. We extend the generalized disturbance to a new system state. Then we can reformulate the output dynamics. To estimate the generalized disturbance, we design a linear ESO. Then we can update the control law. Since this is the compliant link, we also need to address the vibration. We propose to use the deflection feedback to address the vibration problem. We assume this is a singular perturbation problem. Then we can reformulate the closed loop system dynamics. And then we can update the control law. The final control law will address the motion tracking, address the robustness, and vibration suppression simultaneously. We consider a rest-to-rest task for the trajectory planning problem. Here we want to minimize the time, and with these boundary conditions and constraints, it is a bound control based on optimal control theory. And the key is to determine the bound switching time. Different constraint combinations will yield four potential canonical profiles with an analytical solution of the acceleration and velocity. If we consider a particular case, we will know the boundary condition, and this boundary condition will determine which canonical form will be used for this particular case. Then we can integrate with these boundary conditions, offers an optimal trajectory. For the motion testing, we have very accurate motion tracking results. We can also have the vibration suppression. Here we can see on the left figure. For the impact testing, the left one showing the constant stiffness link, the right one showing the variable stiffness link. It turns out the variable stiffness link produces a smaller impact force and a smaller HIC value. To summarize, this work we present a co-design framework with variable stiffness design, nonlinear motion control, and optimal trajectory planning. The motion testing demonstrates successful trajectory tracking and vibration suppression. The impact testing demonstrated the variable stiffness link has a small impact result. This proposed co-design framework offers fast motion and inherent safety simultaneously. Thank you.
So I think we thank again the speaker, and again the questions about the question, you can ask questions in the Slack channel. We introduce the next speaker, that is Roit Nomberg. She will present human-in-the-loop stability analysis of haptic rendering of a virtual stiffness with delay, the effect of arm impedance, by Roit Nomberg and Ilana Niski.
I just share the, you can see the,
Yeah.
Minute. So, okay, hello everyone, I'm Ruth from the Biomedical Robotics Lab of Ilana Niski, and I will present you the work on human-in-the-loop stability analysis of haptic rendering with delay, the effect of arm impedance. So defining the stability boundaries of haptic system with delay is critical, since too narrow and conservative boundaries significantly diminish the effectiveness of static feedback. Currently, the common approach is to analyze the stability of the uncoupled system, meaning analyzing the system without referring to the human operator, and by that, try to define the less conservative control design within this framework. However, it is known that human can contribute to system stability. In particular, in experiments that were done in previous works in our lab, we saw how participants were able to stabilize the haptic system in very high and stable conditions. Hence, our research aim is to analyze what are the stability boundaries of the coupled system, the haptic system plus the human operator. The work I will present here represents the first phase. Here we are referring to the human operator only as an additional impedance to the system. So on the left, there is the conventional scheme of the uncoupled system. Here the operator appears only as an external force. On the right is our alternative scheme for the coupled system. The muscles produce force to move the arm, which is described by inertia, damper, and stiffness components. The arm holds the haptic device, and its movement is translated into movement in the virtual environment. And as a result of this interaction, the haptic system applies forces back on the arm. We analyze the stability boundaries using the frequency sweeping method, which reduces the tracking of the infinite number of routes to the tracking of only the rightmost routes. The rightmost routes vary continuously with the increase of the delay. And when the delay increases, the routes might migrate from the left of plane to the right of plane and vice versa, only through the imaginary axis. Note that because all the coefficients are positive, the two routes of the delay-free version are within the left of plane and the system is stable. This leaves us with three optional stability conditions when the delay increases, depending on the number of the crossover frequency, which are the positive real solutions of the equation. So when there are no positive real solution, no imaginary axis crossing can take place for any delay, meaning the system is delay-independent stable. Where there is one positive real solution, the routes stay in the left of plane until a certain delay value, which began from this delay, the routes cross to the right of plane. And when there are double positive real solutions, the routes are in the left of plane until some first crossing delay, but now they might cross again back to the left of plane with a higher delay, meaning the system can become stable again within higher delays. So we move to the results. And so here we can see the stable delay boundaries of the uncoupled against the coupled system, depending on the virtual stiffness, or in short, the KB. And since the arm's impedance is much higher than the Haptic device impedance, the boundaries of the delay in the coupled system are much wider. Moreover, we see that there is a range of KVE values for which the system is delay-independent stable, and also a range in which we get the possibility of stability and instability sequences. This means that, for example, for KVE equal to 270, the system stays stable until a delay of 100 milliseconds. But if the delay in our system is higher than that, let's say equal to 200 milliseconds, we might get an advantage from artificially increase the delay in the system to a value somewhere between this range, thus returning it to a stable regime. In addition, it is also worthwhile to understand the boundaries dependency on each impedance component. So here, for example, we're examining how changes in the arm's damping and stiffness affect the first delay value in which the system becomes unstable. So the more yellow the color, the greater the range of delay in which the roots do not cross the imaginary axis and become unstable. Where the white area represents the delay-independent stable regimes, and note that here we are assuming the mass of the arm equal to 2 kilograms. We continue with this analysis examining the effect of other arm parameters. So in the second and the third graphs, we examine the effect of arm's mass and stiffness, and in the fourth graph, we examine the effect of the arm's damping and mass. And from here, we can conclude that in the virtual damping-free case, in order to increase the range of stable delays, we prefer high stiffness and damping, but low mass. When adding to the virtual environment a damping component, we will prefer, again, high damping of the arm, but our preference for the arm's mass and stiffness depending on the difference between the virtual damping versus the arm damping. So when the arm damping is lower than the virtual damping, we prefer low stiffness and high mass, and vice versa. And let's conclude. So analyzing the coupled system reveals much broader boundaries and reflects more truthfully the stability results found in the previous experiments. By analyzing the stability based on the frequency sweeping method, we could identify conditions where the Haptic system could be delay-independent stable or could be stabilized by an artificial increase of the delay. And in addition, in environments that are known to us as soft environments, such as the soft tissue of the patient's body, the system can be stable even in the presence of high delays and with an operator with relatively low impedance values. So thank you for the listening. Finish. Sorry.
Thank you for your contribution. And as I said, like there is on Slack now a thread for your paper. So please, all the others, if you can join like our Slack channel in case there are questions, you can reply. So our next speaker is from the University of Stuttgart, Germany. I guess is Eugene Ho. Are you online?
Yes, I'm online.
Okay, very nice. So this is a joint work between the University of Stuttgart and the University of Berlin and the Max Planck Institute for Intelligent Systems in Tübingen. So I let the speaker to share her screen and to present her work. Thanks a lot.
Hi, can everyone see my screen?
Yeah, thanks.
Hi, my name is Eugene Ho, and I'm a PhD student at the University of Stuttgart in Germany, and I'll be presenting my work on natural gradient share control. So robots still require human intervention, and share control balances human control and autonomy. One of the most common paradigms is the linear blending. In this method, the amount of arbitration is dependent on the confidence of the user prediction. However, this has been reported to generate mixed preferences from users, where some users prefer to maintain control authority despite longer completion times. Also, when the user prediction is confident towards the wrong goal, the user has to fight against the assistance rather than gain help from it. So how can we give more control authority to the user? Our motivation comes from vector and potential fields. We can represent the global autonomous robot policy as a vector field over the state space. Here, the obstacles can be represented as a source where the vectors come out from, and goals can be represented as a sink where the vectors join in. Near these regions, the autonomous robot can take more control authority to ensure safety or precision. Elsewhere, the user can keep more control in regions where the field does not locally diverge. We later represent this using the Fisher information matrix. We start by formulating shared control as an optimization problem. The shared control action is chosen to maximize the user's internal action value function while keeping a proximity condition that keeps the shared policy close to the autonomous policy. We assume a linear approximation over the objective and quadratic approximation of the KL divergence. This leads to a new control paradigm for shared control using natural gradient ascent. The state of the shared control system is updated using the previous state plus the inverse Fisher matrix times the gradient of the action value function with respect to the state scaled by the step size eta. And modeling the user's internal action function is challenging. Thus, we utilize the user's action as an estimate of the gradient of the Q function. Now, you might wonder how the Fisher information comes in. The Fisher information matrix, by definition, measures the expectation of the overall sensitivity of a probability distribution to changes of a parameter theta. The Fisher information is the second order derivative of the KL divergence, which emerges by solving the optimization problem using quadratic approximation. In our setting, the Fisher matrix expresses the sensitivity of the policy probability distribution to small perturbations of the state. We estimate this to be the second order Hessian of the action value function. As we consider actions as an approximation of the first derivative of the action value function, the Jacobians of the actions become the Hessian of the action value function. Thus, to compute the second order derivative of the action value function, we use the first order derivative of the actions using the finite difference method. We represent the global robot policy using a neural network that can be regressed over the whole state. This can be easily queried using the trained network. For a pick and place task, we display the ellipses represented using eigenvalues and eigenvectors of the inverse Fisher matrix. The ellipses represent the directions that the user action is stretched along. The user has more control authority over the system where the ellipses are more circle, and when the ellipses are stretched, the robot takes control. We can provide different levels of assistance depending on the cost function that the robot policy optimizes. In the case of multiple goals, we compute the inverse Fisher matrix as a weighted sum over the beliefs. When the intent is not clear, for instance, in these regions, the robot transfers the control authority to the user. So here is a brief overview of our system. I will skip this for time. We define a teleoperation task to assess the efficacy of our method, where the user controls the robot arm to perform pick and tasks using the joystick. We hypothesize that our paradigm allows the user to take more control during the task while ensuring safety and efficiency. And we compare our method with different control methods including direct control and linear blending. Our preliminary results from 16 users show significant improvement over other control methods, and our method was still able to maintain user control while being compliant with user commands. And this is shown especially when comparing the cosine difference between the user commands and the actual shared control commands. So we believe that our results are convincing towards a better user experience, and we plan to investigate more about this in our future work. Thank you very much for listening.
Thank you, Eugene. Very nice talk. Let's fastly move to our next paper. So the paper is entitled Perspective Taking for Shared Control by Connor Brooks and Daniel Zafir from Department of Computer Science, University of Colorado, Boulder. So are you there, Connor?
Yes, I'm here, yeah.
Okay, perfect. The stage is yours.
Okay. All right, so let me start this. Okay, so the motivation behind this idea is situations in which a user is operating a robot without having either perfect knowledge of the robot, so maybe they don't know the robot's joint limits, or they don't know, they don't have perfect knowledge of the environment. So maybe there's, they have like a limited field of view. So in both cases, whether it's information about the environment or the robot, we want to fix problems that arise from a user issuing commands that are based on a faulty perspective. So to flesh out this idea, let's consider a user operating a robot remotely. The user is sending commands to the robot from some remote location here on the left, and the robot obeys those commands in its environment over on the right. Because the user is remote, they don't have access to the robot's environment directly. Instead, their knowledge of the environment is going to be based on their perspective given to them by some sort of control interface. So represented here on the left. So often this user perspective is going to be something like the video feed from a camera mounted on the robot. The user watches this video feed and makes decisions about what actions to take according to that. However, what if there's limitations in what the user can see? What if there are obstacles that are outside the camera's field of view? So in this case, we can see there's some sort of obstacle that's actually in the robot's path, but the user's not going to be able to see it from their perspective, from this camera feed. So the user might issue a command to just go forward to the robot here, not because they want the robot to hit the obstacle, but because their perspective is limiting their knowledge of the environment. So the user may be providing bad commands, but more than that, the commands they provide are going to be bad in some systematic way because their perspective is limited in some systematic way. So we're going to use phi to represent this systematic error in their perspectives. So phi is going to be a mapping from a true state to the state the user has knowledge of. So as an example, if we have something like limited perspective due to field of view, phi is going to take in an actual state, and then for any obstacles outside the camera's field of view, there's going to be some uncertainty about, or we're going to remove those obstacles for this phi mapped version of that state. And when the user provides their commands, they're not really providing them based on the real state. They're providing commands based on the phi mapped version of the real state. We're also going to use this notion of phi inverse, which maps back from the incorrect user perspective state to the real environment. So this mapping is how we introduce knowledge that we have that the user doesn't according to their perspective. So for example, if we do have, maybe by some other sensors or some other information source, the robot does have knowledge about an obstacle that's outside the camera's field of view, phi inverse is going to take that user perspective state and add that obstacle back in. So how do we use this information? Well, the key insight is that instead of assuming that the user really wants us to just apply their most recent command in the real state, we can realize that the user's goal, their local goal, is actually where we would go if we followed their action command from the phi mapped version of the state. So to think about this, like if there's an obstacle in front of the robot, applying the command go forward in the real state would result in maybe the robot tipping over or crashing. But in the phi mapped version of the state, without the obstacle, applying the command go forward just results in the robot moving forward. So the user's local goal, what we realize, is not actually for the robot to tip over, it's to go forward. So then when we're considering how to reach this goal though, we need to actually use phi inverse to map it back to states closer to the real environment. And so this is basically the real version, or the reachable version of the user's goal, with obstacles and things like that added back in. And then from here, we can use various search techniques to choose, what we're proposing is to choose an action that's just going to get us closest to this goal using different distance metrics. And the last thing I want to mention is that this approach only considers the immediate state in action. So we're also working on ways to come up with, to use this knowledge of the user's perspective, phi, to plan ahead for situations in which the user's command is going to be bad. So if there's an obstacle far off that the user can't see, maybe we go ahead and start maneuvering away from it initially. And yeah, so this work is very much early in the algorithmic development stage. And so I'd love to get feedback and take any questions on the Slack channel. Here's my email. Feel free to reach out there on Slack. Thank you.